Today on How It's Made. Pre-ink stamps, guaranteed to leave a lasting impression. Cranberries, more than a turkey sidekick. Putting a high-tech spin on cotton yarn. And road signs, reflective directives. Paid, rush, approved are some of the terms routinely stamped onto documents. Professionals such as engineers have their official stamps too. For years, you had to dab the stamp on an ink pad for each impression. Nowadays, you can get stamps with the ink built right in. The process begins with a design that either the stamp company or its customer creates with standard graphics software. They print the stamp design onto paper using a high-quality laser printer, then place the printout under an imaging camera. They feed in a blank sheet of negative film. Then photograph the printout. 30 seconds later, out comes the negative. The design is light, the background dark. Now they can begin making the mold for the stamp. They apply the negative to a plate of light-sensitive polymer, a plastic-like material. Then they vacuum out the air to prevent defects in the mold. Then they expose the polymer plate to ultraviolet light for approximately 3 minutes. The UV penetrates through the light part of the negative, the stamp design, and hardens the polymer underneath. The rest of the polymer is shielded by the dark portions of the negative, so it doesn't change. A wash cycle then scrubs away this unhardened polymer, leaving behind a perfect mold in the shape of the stamp. Now they cover the mold with a sheet of synthetic resin called Bakelite and put it into a machine called a vulcanizer. The machine heats the Bakelite to 154 degrees Celsius, then forces it into the mold using 2 to 3 tons of pressure. After 4 minutes, the Bakelite stamp is ready. To be more productive, the factory actually molds several stamps at a time. Next comes the built-in ink. They screw the Bakelite stamps into what's called the pre-ink mold, then pour in a mixture of ink and gel. They cover the mold and vacuum out the air, a process that takes 12 minutes. The mold then goes into a heat press for 17 minutes. The press applies 2 tons of pressure to expel excess ink and heats the ink gel to 127 degrees Celsius, transforming it to roughly the consistency of a marshmallow. So it won't overcook, the mold goes onto a special cooling table for 12 minutes. Next, it's set out to cool for another 45 minutes, this time on newspapers, which soak up more excess ink. Finally, they wrap the mold in paper towels and newspapers and vacuum out the last drops of excess ink. Then they quickly seal the back of the stamp to lock the ink in. Now they can cut apart the individual stamps. They glue the stamps by hand onto the base of the stamp handles. Before they're shipped out to the customer, all the stamps undergo a quality control check to make sure they'll leave a lasting impression. Cranberries are one of just a handful of fruits that are native to North America. Before the Europeans arrived, the Indians used them for food and medicine. The cranberry vine is well suited to a harsher climate. It thrives in low temperatures and loves acidic soil that's scarce in nutrients. Cranberries are ripe for the picking in late September. At harvest time, farmers flood their fields to make the cranberries float to the surface. Then they use a machine called a beater. It generates underwater turbulence, pulling the berries off the vines. The beater is suspended from a mobile bridge that's computer-guided to systematically work its way through the entire field. The beater cuts a swath about 7 meters wide with each sweep. Workers move the floating cranberries to one corner of the field, where a pump transfers them to a waiting truck. Along the way, the berries get a preliminary rinsing to remove branches and leaves. At the factory, the truck unloads its cargo. The cranberries travel along a water canal and onto a conveyor belt, then through a cleaning station, where workers use brushes and water jets to get rid of any remaining leaves and branches. Then they dump the cranberries into large bins to be frozen for up to several months. To produce cranberry juice, they defrost the frozen berries in hot water, then mash them, skin, seeds and all, into a puree. They add special enzymes to break up the pectin molecules, making the puree less viscous and therefore easier to press. The press processes 8 tons of puree at a time. That's the weight of 1.5 elephants. It takes 3 to 4 pressing cycles to extract all the juice. The juice then goes through a sophisticated filtration system. The 216 filters remove any plant particles or bacteria larger than 1 micron. A micron is 1,000 times smaller than a millimeter. Then they evaporate the water until the juice is 10 times more concentrated. Cranberries not destined for juice go through a grading process. Undersized berries drop down through the holes of a giant sifter. The bigger cranberries move on to the grading table, where workers remove any that are substandard. An electronic sorter then scans the remaining cranberries for color, signaling an air gun to blow any reject berries off the production line. The rest move on to the packaging department or continue down the line to be dried. Cranberries destined for drying are automatically seeded, cut in half, and pressed, then soaked in a sugar and water solution to make them sweeter. The side-to-side motion of the conveyor belt spreads the berries thinly so that they'll dry evenly. The hot air dryer subjects them to temperatures varying from 30 to 80 degrees Celsius. After about 3 hours, the cranberries come out looking like this. As you sip your cranberry tea, ponder this. Cranberries are a source of potassium and vitamins A and C, and drinking cranberry juice can prevent and treat urinary tract infections. Twisting plant or animal fibers into yarn dates back to ancient times, when people fashioned primitive spindles out of sticks. Around 500 BC, the spinning wheel was born in India. Today's factories have fully automated spinning machines that work on the same principle as a spinning wheel. This is a 2-ply commercial yarn, the kind factories use to weave fabric for making jeans and tops. It's made from large bales of raw cotton. Cotton comes from a plant, so naturally some leaves and stems are mixed in with the cotton fibers. To remove them, the first machine passes over the bales and removes a 5mm layer of cotton, then sends it through a duct system to the blending and cleaning machine. That machine processes 500 kilograms of cotton per hour. The cotton comes out evenly blended and cleaner, but still not clean enough. So it goes into a second cleaning machine, which finishes the job. Now the cotton goes through what's called a carding machine. It has huge rollers with wire teeth. They comb out the tangled fibers and line them up in parallel rows. The machine also discards any fibers that are too short to process. Next stop, the coiler. This device takes the rows of fibers and forms them into a thick and loose first stage yarn called sliver. The slivers move on to the drawing machine. It lines them up 6 at a time and draws them out, stretching them to form a second stage yarn. Then a machine called a roving frame stretches this second stage yarn, strengthening it by thinning it out until it looks like this. This third stage yarn is called roving. Depending on the type of yarn they're making, it's anywhere from 3.5 to 16 times thinner than sliver. They now stretch the roving up to 30 times thinner, which strengthens it even more. The yarn is finally finished. Now they have to transfer the yarn from all these small spools onto huge industrial-sized cones, 20 spools to a cone. One transfer method uses the winding machine. It winds the yarn from the first spool onto the cone. Then it automatically takes the back end of that yarn and attaches it with a knot to the front end of yarn from the next spool. It winds it onto the cone, then attaches the back end to the front end from the next spool, and so on. As each spool empties, the machine automatically discards it. And while all that winding's going on, the machine's optical sensor, that white object you see crossing the screen, does a quality control check. If a portion of yarn doesn't meet specifications, the winding stops, the machine cuts off the offending portion, then reconnects the ends and resumes winding. This is air jet spinning, another method of making yarn from slivers and winding it onto giant spools known as tubes. A suction tube grabs the front end of one spool and connects it to the back end of the previous one, again with a tiny knot. Before fully automated machines like this were invented 50 years ago, all that knotting had to be done by hand. The thin finished yarn is 200 times lighter than the thick first stage yarn that came out of the carding machine. From start to finish, spinning this yarn has taken 48 hours. You might not have noticed, but road signs have undergone a subtle change in recent years thanks to advances in technology. Today's signs are more reflective than ever. You can actually read them in the dead of night, even when the only source of illumination is your car's headlights. The earliest road signs were crude. A stick in the ground or a heap of stones to mark a route. In the Roman Empire, stone posts were erected along roadsides at regular intervals, indicating the distance to Rome. Centuries later, stone marker systems gave way to wooden cross signs pointing in several directions at once. The international system of road signs we know today came out of the first International Road Congress held in 1908. The process of manufacturing a road sign starts with a computer. The government strictly regulates the specifics of the design and requires a certain degree of reflectivity. The computer's specialized software guides a machine to cut the design on a sheet of film. Once the design is cut, workers carefully peel off and discard the pieces. What's left is a film stencil of the sign, in this case, a French stop sign. They inspect it for defects, then prepare a screen of polyester fabric that they'll later use to print the sign. They start by coating it with a thin layer of light-sensitive emulsion. Once the emulsion's dry, they adhere the film stencil, using vacuum pressure to flatten it and get rid of any creases or air bubbles. Then they expose the screen to an intense 6,000-watt light for 7 minutes. This activates the emulsion on the lettering and area outside the octagon, what's not shielded from the light by the film stencil. This exposed emulsion hardens, plugging the minute holes between the screen's fibers. After rinsing, you see the result. Elsewhere in the factory, meanwhile, workers cut the aluminum panels on which the signs will be printed. Using a punch press, they round out the edges and make holes for the bolts that'll later attach the sign to the post. They stamp on the company name and the year of manufacture for warranty purposes. They immerse the panels in a chemical bath to remove grease and other residues. Then they rinse off the panels and dip them in an acid solution that seals the metal to make it better withstand harsh weather. Next, they laminate the aluminum panels with a film containing minuscule glass particles. This film will make the sign reflect in the dark when light hits it. Then they cut the panel to the final shape. Now they can finally print the sign. The process they use is called silk screening, although the fabric screen, as you saw earlier, isn't actually silk, it's polyester. The machine forces the ink down through the screen onto the panel. The ink penetrates through the open fiber holes of the octagon, printing the red background of the stop sign. But it can't penetrate through the blocked fiber holes of the lettering and area outside the octagon, so those remain white. The freshly printed signs pass through a dryer at 66 degrees Celsius for 5 minutes. To produce street signs, workers first laminate aluminum panels with reflective film for the background color. Then either silk screen the street name or apply self-adhesive reflective lettering. But it's back to the silk screening process for printing multicolored signs. Workers print them one color at a time with a drying cycle between colors. All the film stencils are carefully stored for future use. The printed signs go into an oven for a final curing at 176 degrees Celsius, an hour for a one-color sign, a half hour per color for a multicolored sign. The ink is transparent enough not to block the reflective film underneath. Therefore, the entire sign, not just the lettering, is highly reflective. That maximizes the sign's visibility, thereby minimizing the excuses drivers can come up with for not heeding it. Today on How It's Made. Firefighter boots. What's hot in footwear? Garden tools. You'll get the facts in spades. Automated machines. Our annual tribute to those moving marvels. And gypsum board. We're giving this story wall-to-wall coverage. Firefighters need boots they can pull on lightning fast to get to the blaze as quickly as possible. Those boots have to be fire resistant, of course, and waterproof. They have to provide good grip for climbing ladders and be sturdy enough not to puncture when stepping through sharp debris. Firefighter boots start out as a chunky block of rubber. The first step is to put the block through a mill. It passes through the rollers over and over again until it gradually flattens and thins out. Workers then add chemicals, anywhere from 15 to 35 different types, depending on the model of boot they're making. The rubber formulation is what makes the boot fire resistant. Once the rubber is smooth and malleable, about the consistency of modeling dough, they form it into sheets from which they'll cut the various pieces that make up the boot. They feed this sheet through rollers that imprint vertical lines on the rubber. They'll cut the sheet along these lines to make the strips that run down the back of the boot. From another sheet of rubber, using a handheld die, they cut one layer of the multi-layered sole. They run an extra thick sheet of rubber through rollers that imprint a tread pattern. Then workers cut out the bottom soles. They mark the boot size on the bottom. Using yellow rubber, they cut out the boot's toe cap covers. The boot's leg has a stiff lining to prevent it from wobbling. Workers cut it from a rubber-backed cotton fabric following a pattern. Once all the pieces are cut, workers can assemble the boot on a form. They start with the lining, wrapping it around the front and gluing it closed at the back. Then they glue on the insole. For this model, it's made of rubber-backed felt. They secure the lining seam and seal it with one of those rubber strips we saw earlier. Now, the vamp, a piece of felt reinforced with a thin layer of rubber. This gives the boot strength. Next, the toe cap sponge, made of rubber compounds. When they cure the boot, the sponge will inflate and hold this steel toe cap in place. To protect the firefighter's feet when walking through sharp debris, a steel arch and a steel sole. Next, an adhesive-backed toe cap cover. Then a felt sole to protect the firefighter's foot against heat. It has a steel arch for stability when the firefighter climbs the ladder. After applying a rubber heel reinforcement, they cover the lower part of the boot with yellow foam for insulation. They secure it using a strip of rubber. Now they finish the bottom of the boot in black rubber. They reinforce the back and sides in yellow rubber and finish them off in black rubber. Next comes the yellow toe cap. Then a rubber pad to protect the front of the boot when it rubs against the rungs of the fire ladder. Now the bottom sole. They use a press to seal it in place. Rubber bonds to rubber under pressure. They apply a rubber trim around the bottom, using a small roller to press it in place. Workers then press all the seams to ensure they're well adhered. Then it's into a vacuum machine for about 4 seconds to create an airtight bond. Finally, the boots go into a giant oven that heats them to 140 degrees Celsius. An hour and 45 minutes later, the rubber is cured and hardened, and all the pieces have fused together. These boots are ready to take the heat. Anyone with a green thumb knows that it takes both skill and patience to make a garden flourish. It also helps to have the proper tools on hand. An avid gardener's arsenal can contain everything from shears, trimmers, and pruners to rakes, hoes, and spades. The handles of these garden tools are made of white ash, a sturdy wood that can withstand the force of shoveling, digging, or raking. These dried ash dowels measure 0.5 meter to 2 meters long, depending on the tool being made. They first enter what's called the chucking line, where specially designed automated machines shape them into handles. The first operation rounds the dowels to the required diameter, 4 centimeters or so, depending on the tool. The next operation cuts the dowels to the required length and profiles their ends. Two chucking heads, one on each side, carve the ends simultaneously. One shapes the bottom of the handle to fit the tool's blade. Certain blades go over the wooden handle while others go into it. For those inserted blades, another chucking head hollows out the handle. Meanwhile, the chucking head on the other side rounds off the top of the handle. The finished handles spin against a sanding belt as they exit the chucking line. This smooths the surface of the wood, preparing the handles for a coat of protective varnish. High-end shovels and spades have what's called a steel D-grip, a steel handle grip with a wooden insert. An automated lathe first shapes a piece of ash to the right length and profile. Then an automated drill pierces a hole. To make the sides of the grip, workers begin with 2 pre-cut pieces of steel called blanks. They place them in a manually operated press that shapes them in a 2-step process. They use the heat of a strong electrical current to melt the steel and fuse the pieces together. This is called resistance welding. Next, they feed a steel rivet through the sides and wooden insert and fasten everything together. Elsewhere in the factory, meanwhile, a heated forming machine stamps out the steel blanks that workers will shape into blades. A robotic arm loads the blanks into an oven. In a mere 4 minutes, the oven heats the steel to almost 1,000 degrees Celsius. This intense heat makes the metal malleable. Workers then take out and shape one blank at a time. They have just a few seconds to form the steel before it cools off. The first press forms the blade, in this case a shovel, and a partial socket. Then the second press closes the socket. They quickly submerge the blade in lukewarm water to cool the metal down. By now, the steel is extremely brittle, so the blades go into what's called a tempering furnace for 15 minutes. This alters the metal's internal structure, restoring its strength. The steel D-grip, meanwhile, has been cleaned and painted. Workers insert the wooden handle and nail the parts together. On the other end, they attach the blade, which by now has been varnished to prevent corrosion. After drilling a hole through both the metal and the wood, they fasten the blade using a rivet if it's a high-end tool, a nail if it's a budget model. These hot-off-the-press garden tools are finally ready to put in a hard day's work. A couple of centuries after the Industrial Revolution, mass production met automation, a match made not in heaven, but in high technology. In this special segment, How It's Made honors the automated machine with this moving tribute. It's called gypsum board or drywall, and chances are your walls and ceilings are made of it. Years ago, it replaced plaster as the wall material of choice. Workers just mount the sheets onto wood framing, plaster the joints, then sand and paint. Gypsum is a natural mineral. Since ancient times, it's been mined to produce gypsum plaster. In fact, there's gypsum plaster in Egypt's pyramids. In 1894, a man by the name of Augustine Sackett patented a board made of gypsum which he called plasterboard. But it didn't become the norm in construction until the building boom that followed World War II, when busy contractors abandoned plaster in favor of this faster and cheaper way to build walls. The process of making gypsum board begins at the quarry, where crews mine the gypsum, a soft rock. The loaders dump their haul into what's called an apron. The apron channels the gypsum onto a conveyor, breaking up the big chunks along the way. From there, it's into a giant rotating drum. Within 8 minutes, this hot air rock dryer removes 5 to 10% of the moisture, turning the gypsum white. Next stop, a gas-fired silo called a kettle. It cooks the gypsum at 150 degrees Celsius until most of the remaining moisture evaporates. Feeding that kettle, a mill that grinds the lumpy rock into what's called stucco, a fine powder the consistency of wheat flour. In a mixing tank, meanwhile, workers combine water with several powdered chemicals and minerals, and a chemical soap. The dry additives give the board the required structure, while the soap creates air bubbles to make the board lighter. In a separate machine, they mix the stucco with an accelerator to make the gypsum set faster. Now they combine the two separate batches, creating a mixture called a slurry. It looks like thick white soup. Now they'll form it into gypsum board, which is basically a slurry sandwich. The bread is this thick, heavyweight paper. As the roll unwinds, creaser wheels, as they're called, score a line about 3 centimeters in from both edges. Then a machine evenly spreads the slurry like a sandwich filling between the top and bottom sheets of paper. Then the paper folding operation, most of which is a company secret and off limits to our cameras. They fold the edges along the score lines, the bottom edges upward, the top ones downward, gluing them over the bottom ones to trap the slurry inside. Drops of water smooth out any ridges, ensuring a smooth and even fold. Forming plates then shape the folded edges into straight sides. An optical sensor checks the depth of the board's recess. That's where you put the joint tape to connect one board to the next when you're building a wall. The forming station spews out 305 continuous meters of gypsum board at a time. A cutter now chops that mega board into whatever length board they're producing in this run. As the boards exit the cutter, automated prongs flip them recessed side up. Since the recessed side will be the wall surface, they don't want to risk damage by having it travel face down on the rollers that lead to the drying station. This gas-fired hot air dryer is kind of like a multi-level parking garage. It's more than 150 meters long and has 8 decks. The factory can cure hundreds of boards at a time. It takes 40 minutes to move through the dryer's 4 temperature zones, which start at 350 degrees Celsius and get progressively cooler to 150 degrees. The boards are sold in pairs, so the machinery stacks them in twos, then tapes them together. The tape bears the brand name as well as the size and thickness of the board. Standard lengths range from 8 to 14 feet, and the most common thicknesses are 1/2 inch and 5/8 of an inch. In this industry, imperial measurements are still the norm. The tape also tells the consumer what type of gypsum board it is. There's standard drywall for building walls in homes. There's a moisture-resistant version for humid areas such as bathrooms. There's also fire-resistant gypsum board, usually required by law for commercial buildings. Today on How It's Made. Horse-drawn carriages, craftsmanship that's hot to trot. Artificial eyes, the product of artistic vision. Dog and cat food, it's not the slop it used to be. And mirrors, when image is everything. Nothing takes you back to the past quite like a ride in a horse-drawn carriage, a timeless vehicle in both appearance and construction. Building one, even today, still requires the expertise of several traditional craftspeople, from ironworkers to wheelwrights. The carriage's turning mechanism is a 5th wheel that's positioned horizontally above the 2 front wheels. Workers weld the 5th wheel to the carriage's steel frame, then weld the boarding steps to the frame. Until now, the frame has been positioned upside down. Now they turn it right side up to install the driver's seat. First, they measure carefully to ensure it's perfectly centered. Then they solder it in place. Once the frame is complete, it goes through an acid wash to remove any residue. Then they buff the solder joints to smooth out their surface. The carriage has drum brakes. Workers install them onto the axle, then assemble the steel springs that make up the suspension, and bolt them onto the axle as well. Next, they connect the brake line. Then they install the whole assembly under the carriage's frame. Like in the olden days, they make the wheels out of wood. Metal isn't flexible enough to withstand bumps in the road. They use ash because it's a very hard wood that also doesn't rot easily. Workers position 16 spokes around a steel hub. They clamp the spokes in place, compressing them against the hub. Then they secure them with nuts and bolts. Next, they mark the spokes in 2 places. The first line shows how long to cut each spoke. The second line, how far to dowel the end. To form the dowel, they first shape the end into a cone. Then the cone into a dowel. Those doweled spokes will fit into corresponding holes they now drill into 2 semicircular strips of wood. The strips form what's called the felloe, the round part of the wheel. Workers tighten the hub, then press a steel band called a channel against the felloe. They cut the channel to size, then solder the ends together. Then they buff the joints smooth. Next, they drill 8 holes through the channel, then using a tapering tool, thread the holes to fit the bolts that bind the channel to the felloe. Finally, they tighten the bolts with a special gun. The tires are made of rubber. They contain 2 steel wires to hold them in place over the wheel. Workers grease the channel of the now painted wheel so that the tire will slip on easily. Then they mount the wheel on the automated tire installation machine, which pulls on the wires, installing the tire tightly over the wheel. They weld the wire ends together using bronze solder this time for a stronger joint. Then, here comes the high-tech part, They bang the wheel on the ground 4 or 5 times until the distance between the tire ends closes, covering the welded wires inside. A tap of the hammer, followed by a final bang, ensure the tire joint is secure. Now they can mount the wheels onto the axles and install the axles under the body of the carriage. After testing the 5th wheel and the brakes, it's time to apply the finishing artistic touches. All they need now is a little horsepower. The ancient Romans and Egyptians fashioned artificial eyes out of painted clay. By the 1500s, Europeans started making them out of enameled gold, and soon out of glass, which remained the norm for hundreds of years. Today, most artificial eyes are made of acrylic. If you've lost an eye in an accident or to a disease, a specialist known as an ocularist can fit you with an artificial eye. You can get a ready-made model or a custom-made prosthesis like the one for which this patient's being fitted. No two people's eye sockets are the same, so the first step is to take an impression. After inserting the impression tray, they inject a material called alginate, filling the entire socket cavity. After 90 seconds, the alginate sets and they can remove the hardened impression. They place the impression in a mold and pour in a type of plaster. When the plaster has hardened, they remove the impression tray and then the impression itself. What's left in the mold is a plaster replica of the socket. Now they put a wad of acrylic plastic dough into the mold, lock the mold into a press, and submerge it in a high-pressure curing unit for 25 minutes. Then they cool the mold in cold water. Here's the original impression compared to the acrylic model they've just cast. This model is called the fitting shape because they use it to fit and mark the positioning of the fake iris. They accentuate the markings, then attach a peg with a drop of wax. The peg indicates the natural angle of the iris when the patient is looking forward. Next, they add wax around the perimeter to enlarge the fitting shape. This excess will give the ocularist some play afterwards for the final sizing. Now they take this marked and enlarged fitting shape and make a plaster mold. They'll later use that mold to cast the actual artificial eye. But first, they have to make the iris. They take a curved black acrylic disc and paint it as realistically as possible with high-quality artist's oils. The patient has to be present so they can match the real eye. Next, they glue an acrylic cornea with an appropriate size pupil onto the painted iris. At this point, the artificial iris is 13 millimeters in diameter. If the patient's real iris is smaller, they trim down the replica to match. The iris then goes into the plaster mold, covered with white acrylic dough. After the same high-pressure curing process as before, out comes the artificial eye, covered with excess white acrylic. They trim off that excess and the peg, using a grinding tool and a cutter. This refines the shape and exposes the iris buried underneath. They smooth the surface against a grinding stone and verify the measurements. Then, using hard coloring pencils, they add finishing touches to the iris and draw blood vessels. They label the eye with the patient's initials, then apply an acrylic coating to seal the pencil marks. To create veins with some dimension, They use the same acrylic coating to stick on some delicate silk threads. Once they're satisfied the artificial eye is a perfect match, they seal the artwork with another acrylic coating. Once that cures, they polish the eye to a shine with a cotton wheel. The shapes and colors of artificial eyes are endless because patients' eye sockets and irises greatly vary, as do their scleras, the white of the eye. This artificial eye, or ocular prosthesis, is ready. The final step is to ensure that the fit is perfect. The patient's ocular muscles attach to the implant, enabling his artificial eye to move in unison with his real eye. So much for feeding Fido scraps from the table. Today's pet food is the stuff of sophisticated nutritional science. It's about protein, carbohydrates, vitamins, minerals, a well-balanced diet. Want to bet some dogs and cats eat healthier than their owners? The formulas for dog and cat food differ because dogs and cats have different nutritional requirements. Cats, for instance, need more fat and protein in their diet than dogs do. But the basic ingredients that factories grind up to make dog and cat food are generally similar. First, corn kernels. Then cereals such as barley, wheat, and rice. Workers weigh the ingredients, grind them in a mill, then combine everything in a mixer until they have an even and well-blended powder. A machine called the extruder transforms that powder into bite-sized pieces of pet food. It steam cooks the mixture, then forces it through dies at high pressure. The dies shape it, the way the tip of a pastry bag shapes icing into swirls or roses. Check out this dog bone die. As the continuous stream of shaped mixture exits the die, a spinning knife cuts it into pieces. The company has different dies to produce different shapes. This is a batch of round pieces. Next stop, a hot air dryer for 25 minutes. It heats the pieces to 149 degrees Celsius to draw out the moisture, then cools them at room temperature. Once the pieces exit the dryer, they enter a revolving drum where they're sprayed with fat and flavoring. The fat is designed to add food energy, while the flavoring gives the bland pieces an appetizing odor and taste. Appetizing for the pets, that is. The rotation ensures the pieces get coated evenly. From here, the pieces go into storage silos. When they leave the silos for bagging, the machinery screens out any crumbs. The pet food industry has made some interesting observations about the likes and dislikes of its four-legged clientele. Apparently, cats and dogs aren't crazy about food that's too dry, too hard to chew, or too mushy. If the pieces are too small, they'll swallow them whole without chewing and not digest them properly. But if the pieces are too big, they'll gag and get turned off the food altogether. In the packaging department, automated scales weigh the exact quantity per package. This batch is destined for 3-kilogram bags. The package sizes range from just 400 grams all the way up to 20 kilos. Shelf life is from 12 to 16 months, depending on the formula. Pet food experts say dogs and cats prefer food with a fattier content and a combined meat and cereal formula over just cereal alone. But too much meat flavoring can turn them off. Cats, as a rule, are more particular. They favor more acidic food, while dogs tend to have a sweeter tooth. And you thought kids were fussy eaters. No bathroom's complete without one, and any parent will tell you that no teenager can survive without one. Mirror, mirror on the wall, how do they make you after all? Well, how it's made is about to show you. But first, let's reflect on the history of mirrors. The earliest mirrors were curved pieces of highly polished metal, such as brass or bronze. They're even mentioned in the Bible. Then in the 14th century, the Venetians invented very crude glass mirrors that reflected off a metallic backing. They later perfected this technique using an amalgam of tin and mercury. Eventually, the secret of mirror making spread to other cities. By 1835, a German chemist developed the silver-backed mirror that we know today. A mirror starts out as clear glass. A robot lays each panel horizontally on a conveyor belt, which transports it to the washing station. There, sprayers blast the glass with water and cerium oxide, a powder derived from a type of earth. Rotating brushes scrub and polish both the top and bottom surfaces, removing oils and other contaminants. This washing process takes about a minute per panel. Next, sprayers rinse the glass with piping hot demineralized water. Demineralized because the minerals in plain tap water would damage the metals they apply next. The first metal is liquefied tin, which goes on what will be the back of the mirror. It allows the second metal, silver, to adhere because silver won't stick directly to glass. The silver is also in liquid form, mixed with a chemical activator. Within seconds of interacting with the tin, it hardens, and as it does, you begin to see a reflection. It's this silver backing that transforms clear glass into a mirror. Sprayers rinse off the excess silver, which gets recycled back into the system. The factory will seal this silver backing with 2 coats of paint. Paint by itself, however, isn't enough to protect the silver in the long term, so they first spray on a layer of copper. Sprayers rinse off the excess copper, then the panel passes through a dryer at 71 degrees Celsius. This evaporates the moisture on the surface in just 75 seconds. Now the panel passes copper side up through what's called the curtain coater, a machine that runs a continuous curtain of paint across the conveyor belt. With its fresh coat of paint, the mirror then passes through an oven heated to 99 degrees Celsius. After 1 minute and 45 seconds, the paint is cured. Now the second coat of paint. There's no reason for the different color other than to differentiate the coats. The curing period this time is twice as long and at a higher temperature, 118 degrees Celsius. After an acid wash to remove any metal residues, they stand the panel upright to inspect it. If they find a fault, such as a bubble in the glass, they cut that portion out. The factory now cuts these large panels into whatever size and shape the customer has ordered, using a special mirror cutting machine that's precision guided by computer software. It scores the mirror using a carbide wheel. Carbide is a strong metal. To make round mirrors, the machine first scores the panel into squares. Then in each square, it scores a circle. Using special tools, workers separate the squares, then the circles. To make beveled mirrors, they use what's called the shape bevel machine. First, it carves out the edge, then polishes it to a shine using concentrated cerium oxide, a stronger version of what they used earlier to clean the glass surface before plating it with metals. Mirror factories also ship whole panels to shops that do the cutting themselves. A fragile feat that's certainly not for the superstitious.